When conducting a statistical study, it's very important to choose an appropriate sample size. Right now we've been talking about confidence intervals. And when constructing a confidence interval using sample data, knowing how large to make that sample is very important, because we've seen that as the sample size increases, the margin of error goes down. So you might be thinking, well, let's just take a really large sample every time, and then it won't matter. Well, there are two things to think of there, at least two things to think of there. Number one, what does really large mean, right? Different situations might make really large mean different things. And second, when you're doing a statistical study, there are cost constraints. And so we want to use a large enough sample without using a larger sample than we actually need. If we look at our margin of error formula, we can solve it for n and then use it to figure out how many things should be in a sample for a particular situation. So to start off with, my goal here is to solve for n. So to start, I'm going to square both sides because n's under this square root and I want to get rid of it. So I'm going to put the z sub alpha over 2, the critical value, in some brackets here just so I know I'm squaring that value too. But when I square the square root goes away and I get a p hat times q hat all over n. So what I'm going to do now is multiply both sides of that equation by n. And that would give me n times e squared, so n times a margin of error squared equals z sub alpha over 2 squared times p hat times q hat, right? Because the n's cancel. And now I would see that n is equal to z sub alpha over 2, my alpha disappeared there, my critical value squared, p hat times q hat, all over a margin of error squared. So, if we find values to plug in for z sub alpha over 2 squared, well, that's easy. That's associated with a confidence level. So we pick a confidence level, we know what to plug in there. We have to talk about what to plug in for p hat and q hat, because we haven't done the study yet, so we have to figure out something to plug in there. And then what we do is we choose a margin of error. We say we want our margin of error to be no more than 2% or 3%, and we use that in this calculation. Well, the p hat and q hat, those are harder to know anything about. And so there are two rules. The first rule is if you don't know anything about p hat and q hat, and if we just pretend for a moment that those are the sides of a rectangle, well, let's see. The area of that rectangle would be p hat times q hat. And anytime I see two numbers in mathematics multiply together, I could actually kind of pretend they were the area of a rectangle with those two lengths. And it turns out that if you have two unknown lengths like these, and these ones have to add up to 1, by the way, because they're complementary probabilities, in that situation, the thing to do is to actually make your rectangle a square. And that will be the rectangle with the most area. So what I'm really arguing here is that the largest thing p hat times q hat can ever be is what you get when p hat equals q hat. Well, if p hat equals q hat, it means they're both equal to 0.5. Because they have to add up to 1. If they're the same thing, it has to be 0.5 plus 0.5 is equal to 1, which would make p hat times q hat 0.5 times 0.5, and a half times a half is a fourth, 0.25. So that gives us one rule. If I don't know anything about p hat and q hat, this formula becomes this. So if p hat is unknown, which makes q hat unknown, n is equal to the sample size we should use, z sub alpha over 2 squared times 0.25, that worst case scenario that p hat and q hat are as large as they possibly can be, all over e squared, the margin of error squared. Okay, well, there are situations where we might have estimated p hat. Maybe there was a pilot study. And a pilot study is just a smaller study, and so there's like some estimated value of p hat, and in that case, we just use it. And the nice thing there is if we have estimated p hat doing a prior study, this can decrease the amount of things we need in our sample for this study because this is a worst case scenario. All right, so those are the two formulas that we can use to estimate a sample size. In our next video, I'm going to do an example where I use both.